Good morning to all of you. I welcomes to all in our lecture series on solid state physics. Today in this lecture we are going to be discuss about the Van Laue treatment, or it is called as Laue's equation. These equations or the Laue's equations, whatever we are going to be discuss or going to be derive, these equations required to know or to find out or to evaluate the diffraction conditions, or we can say the maxima, or in which way we are going to find out the diffraction from the lattice is going to be maxima. Regarding that, we have been already discussed the Bragg's treatment or Bragg's law, or the so-called Bragg's condition, that is 2d sin theta equal to n lambda, where lambda is nothing but your wavelength of X-ray and d is the interplanar spacing, this one, and this is one plane and this is another plane, and when the X-ray is going to be incident and these P dash Q dash are the so-called diffracted beams, and these two beams is going to be interfere with each other and going to be produce its constructive interference or maxima. Condition of maxima has to be followed by the Bragg's condition, that is 2d sin theta equal to n lambda. Here in case of Bragg's treatment, Bragg has been considered that the planes from where the X-ray has to be reflected and going to be interfere with each other. But in case of Van Laue treatment, Van Laue have been considered that X-ray has to be interact with individual atoms. The figure I am going to be explained in detail, so should not be worried about that. Here A and B has been considered as two individual atoms. So in case of Bragg has been considered that the planes where X-ray has to be fall or incident and going to be diffract, but here Van Laue has been considered that X-ray is going to be interact with individual atoms. Let this is A and B are the two atoms, and when they are going to be diffracted, and in what will be the condition that interference is going to be the maxima, or the constructive interference is going to be happens. If constructive interference is to be happens, then we can get the diffraction pattern. Okay, so that conditions are nothing but called as the Laue's equations that we are going to be derive. So I will be suggest to all of you that at least you have to go for this one, Bragg's treatment and Bragg's law. Previously we have been given, and I will give the link of this explanation in this in the description of this present video, so you can go through this one, Bragg's treatment and Bragg's law. Okay, so now we have to start the Van Laue treatment or Laue's equations. So as I told to you that in case of Van Laue treatment, what he has been considered, or Van Laue treated the phenomenon of diffraction by considering the scattering of X-rays from individual atoms in the crystal. So individual atoms, here two atoms he has been considered. Let this is A and B, and the distance between A and B is R. Here R is the position vector from B to A, and the distance will be R. Okay, another thing I am going to be suggest to you, all of you, that this figure you have to do perfectly in your note, perfectly as I done, you have to do perfectly. So you have to pause the video and you have to draw the diagram perfectly, because our sir told in my PhD time that the figures is going to be tells out all the things. in the physics, because these are all the geometries. So angles, if will be not perfect, the physics what we want to understand or what we want to explain, that will be mismatch, or that could not be exactly understood by us, or could not be exactly explainable. So the figure will be tells many things. the छवि बोलता है, जो बोलते हैं हिंदी में छवि बोलता है, ठीक है. तो diagram should have to be perfectly, has to be done by you. So now here von Laue, what he has been considered, he has been considered the two atoms A and B are situated with the distance r. Okay, this much I have been studied here, this one. And the direction of diffraction maxima will be found by recombination of scattered or diffracted X-rays. So the direction of diffraction maxima, so here these are the scattered beam, or we can say reflected beam, or we can say diffracted beam. These two N1 cap and N1 cap named as incident beam. When these two rays, X-rays, will be interact with A and B, they are scattered in this way, or reflected in this way, or diffracted in this way, which is named as N2 cap and N2 cap. So towards A, the ray is named as N1 cap. From A, the scattered beam is named as N2. Likewise, B atom is also going to be considered. N1 will be incident, and here N2 cap is the scattered beam. Okay, so here these two rays is going to be interfere with each other and going to be produce if maxima or constructive interference, then we can get the diffracted pattern, or we can say that at a specified angle, with a specified angle, suppose here we have a sensor, so at a specified angle, these two rays is going to be interfere with each other and will be produce the maxima. The same thing it has been written, that the direction of diffraction maxima, will be found by the recombination of scattered or diffracted rays. Recombination means interference of scattered and diffracted X-rays. Now the diffraction maxima appear in some specific direction. What I told to you here, that a specified direction we can found these two rays are going to be interfere constructively. And so if I am going to be change the position of this is a sensor, this is I sensor, suppose this is the sensor. If I will be move the position of the sensor, may not we are going to be found the constructive interference between the two rays, but at this particular place it can be detected, this sensor will be detected that these two rays are going to be interfere constructively. Okay, so this is written like that: the diffraction maxima appears in some specific directions which obey certain conditions, that is known as Laue's equations, that we are going to be derive in this video. From Laue's equations, the validity of Bragg's treatment, Bragg's law, can be derived. From Laue's equation also, the validity of Bragg's law can be also derived. So this will be a one type of long question for the B.sc honor students. May be asked that you have to explain the von Laue treatment for 6 mark, and if it will be asked as also you have to verify the validity of the Bragg's law from the von Laue, then it will be asked as 7 to 8 marks. So carefully you have to watch this video. Now I am going to explain this writing, second page writing with a figure. Okay, consider two arbitrary atoms A and B in the lattice from which incident ray beams scattered as shown in the figure. So this is our figure. So A and B are the two atoms where the rays, X-rays, incident beam is going to be scattered in this way. the incident beams and the distance between A and B is r. The distance between A and B or B to A will be r. This is r vector I have given. So its modulus will be nothing but its distance. Okay, I am going to do a small zoom now. Okay, now here n1 and n2 be the unit vectors in the directions of the incident and scattered beams respectively. So this is n1, indicates or represents the incident. This is represent the incident on atom B. This is represents the incident ray on atom A, and this n2 and this n2 cap, n2 cap represents the scattered beams respectively. Okay, now now 2 theta be the angle between n1 cap and n2 cap. So this angle is nothing but 2 theta, because here we can see that if there is no reflection or diffraction from point B, then the n1 ray will be in this way. This dotted line B to B dash also can be called as n1 cap without any reflection or diffraction from point B. So from point B, as it is diffracted along this way or BS direction, or we can say n2 cap, then this whole angle will be called as will be 2 theta, or we can say that diffracted angle will be diffracted angle. Okay, so 2 theta be the angle between n1 cap. See, n1 cap this direction, n2 cap this direction, angle is 2 theta. Okay, now to obtain the conformations of the constructive or destructive interference between two scattered rays. Here the two scattered rays are from A one scatter ray, from B another scatter ray. So in between these two rays may be constructive, may be destructive interference. So to obtain the conformation of constructive or destructive interference between two scattered rays, the path difference between these two rays is required, is essential, is required or essential, because if we can found the path difference between the two rays, that is this is one ray, from this came from here and interacted with atom A and scattered in this way. This ray has came in this way and scattered from B and gone in this way. So path difference between this and this ray will be tells us the constructive or destructive interference between these two rays. So that is essential that we have to confirm that these two rays constructive or destructive interference. Now for that we have to draw the BM and AL perpendiculars to the incident and scattered beams respectively. So now here BM and AL. BM, I have been drawn a perpendicular on the incident ray, and AL another perpendicular I have been drawn on the, this is the scattered ray, on the scattered ray. Now for these two rays up to from this point to this point and from this point to this point at the same distance they have been travelled. Okay, and from A to onwards, from AL to onwards, these two rays also travel the same distance. So what is the extra path? So what is the path has been extra travelled by this ray, that is AM. The extra path travelled by this ray, this ray is B and L. So the extra path travelled between this ray and this ray will be BL minus MA. Again I am going to explain carefully, you have to watch. Suppose this ray starts from here to M, from here to B, this is the perpendicular, both are same distance. Okay, from A to onwards, from L to onwards also they have been travelled the same distance, but this distance and this distance MA and BL not the same distance. So what will be the path difference between this ray and this ray? That will be BL minus MA or AM. Okay, same thing I have been written over here. Then the path difference between the two rays, between the rays scattered from A and B, will be path difference equal to BL minus AM. Okay, now from the triangle BMA, see, and this is the position vector. Okay, B to A is the position vector, means one atom to another atom. This is the position vector. So now consider what I told, that BMA. Yes, another thing I forgot, that here this figure you have to draw over here. Means this is the first page, this is the heading, and you have been written this much writing. Then this figure has to be here. You have to draw this figure perfectly here. I have been drawn separately because I have to explain to you. Only for that, if I will draw here, then many times I have to go back. It will be problem for me for the explanation. So that I have been drawn separately, but you have to do there. Okay. Now the triangle, from the triangle BMA, what is the BMA? BMA. See, this is the parallel. These two rays are parallel. So this is one line. So this angle will be this angle. Okay. Sorry. Actually, suppose this is the angle we have to consider, sigma 1. Okay. And this is the angle we have been considered, that sigma 2. So this is the two angle we have been considered. For this triangle we are now considering BMA triangle. So cos sigma 1 will be cos sigma 1. If I am going to write cos sigma 1, BMA, cos sigma 1. Cos sigma 1 will be how much? AM by R. This is the AM, this is the 90 degree. Perpendicular, this is the 90 degree. This is the sigma 1. So AM is the base by AB. AB is the distance, nothing but R. So AM by R. Or AM will be equal to R into cos sigma 1. So this is AM can be written as R dot n cap, because the sigma 1 is the angle between this ray and this vector and this vector. So I can write R dot n cap, instead of write R vector modulus cos sigma 1, I can write R dot n cap. Okay. Now similarly, if we have to consider BLA triangle, where is the BLA triangle? BLA triangle. Likewise also we can consider, that will be BL. This will be nothing but R dot N2 cap. Okay. R dot N2 cap. Okay. Now these two things we have been got over here. This will be required for measuring the path difference. Now whenever I am going to put AM value over here and BL value over here, then what I am going to get? I am going to get the so-called path difference will be R dot N2 cap minus R vector is there, dot product is also there, N1 cap, or it can be written as R vector dot N2 cap minus N1 cap. Okay, first you go through that video, then you have to draw the figure and you have to write the note. You have to pause the video, wherever you want you can write the note. First you go through full the video. Okay, here, because why I am going to say, because many things I have been drawn the figure. If you have to draw initially the figure, you are going to do the mistake. Okay, so first you go through the video full, then you have to go for the writing. Now here n vector, here n vector will be n2 cap minus n1 cap. How it is, see. So this is the atom B, and this is, we can say, the so called one plane from where it has been diffracted. This ray diffracted from B, suppose this is the plane, okay, where the atoms will be placed in this way, okay. And if this atom will be not here, this incident ray will be go in this way. As this atom will be here, the diffracted ray is gone in this direction. So now, if I am going to be draw a vector from here which will be perpendicular to this plane and will be touched to the n2, this vector will be represented as n. So this vector can be equal to n2 cap minus n1 cap, because from B to S, suppose this point I have been named as S, this point is named as P, this is perpendicular because this vector will be perpendicular to this plane, this is dotted plane where the B atoms, like B atoms, will be periodically will be placed over here. You can imagine, okay. Now this vector B dash S n represented by n, capital N, will be, see, vectorially I am going to be, if I am going to consider triangle law, vector addition or subtraction, then this is nothing but n1, this is nothing but n2. Obviously this closing side will be equal to n2 cap minus n1 cap. Same thing I have been written over here. The n vector will be n2 cap minus n1 cap, considering the triangle law for triangle B dash S, okay. Now here n and this n is normal to the reflecting plane. What is the reflecting plane? This is this dotted line which is passed through the B atom. This will be the so called imaginary plane. On this plane the periodic atoms, so here is one atom with a periodic arrangement, the atoms will be here. Here is another atom, here is another atom, here is another, periodically has been placed. In case of Bragg, he has been considered that this arrangement will be considered a plane only, and from incident ray will be fall upon this plane and it will be reflected back and refracted this way. But here one law has been considered, B is one atom, A is another atom, okay. So likewise, if we have to consider this periodic arrangement, so this dotted line will be act as a plane, and this n vector will be perpendicular to that plane, okay. So here these atoms, whatever I have been drawn, no need to be drawn, okay, no need to be drawn here, only for your understanding purposes I have been drawn. You should not be, I also erased, okay. Now from triangle B dash P, I am going to take this B dash S or n vector is perpendicular to this plane, okay. So this angle is theta, this angle also theta. Now we have to consider B dash P, this triangle. In this triangle, this will be the 90 degree, okay, this will be the 90 degree, this will be the theta. So hence sin theta, if I am going to consider, sin theta is nothing but B dash P, this is theta. Sin theta, if I am going to consider, this will be the height divided by diagonal, that will be B dash, which will be nothing but n1 cap modulus is nothing but 1, because as it is considered as the unit vector. So B dash P by n1 cap modulus is nothing but 1, so hence it will be B dash P. So here B dash P will be equal to PS, because this angle is equal and this is perpendicular, so B dash P plus PS will be equal to B dash S, and B dash P, this distance and this distance both are equal. B dash P, we found that sin theta. So whole distance from here to here will be nothing but 2 sin theta. Let this equation number is 1. Okay, let this equation number is 1. So this is our equation number 1. Now if the path difference is r dot n, whatever we found here, then its corresponding phase difference phi between the two scattered beams is how much it will be? It will be phi equal to 2 pi by lambda into path difference, that will be r dot n. Let this is equation number 2. The radiations scattered by atoms from A and B, whatever the radiation which will be scattered from A and B will be interfered constructively only if the phase difference becomes integral multiple of 2 pi. These things we have been studied in our last semester in the optics. I am going to show you what we have been studied there. Here I am going to show the last answer or end of the derivation of the Young's double slit experiment, whatever we have been studied in our second semester, I think, in the optics. That is, for constructive interference, the condition is path difference. Here path difference should have to be plus or minus n lambda. So if path difference will be plus or minus n lambda, so phase difference will be 2 pi by lambda into path difference, that will be n lambda. So lambda got cancelled, it will be 2n pi or n 2 pi, we can say n into 2 pi. So if the phase difference will be n 2 pi, whatever I have been written over here in your present note, that is the constructive interference only if the phase difference becomes integral multiple of 2 pi. Here we have also studied the same. This is the integral multiple of 2 pi is the condition for your constructive interference that we have been studied in our last semesters. So due to periodicity of crystal, the other atoms placed in the same direction, that means what I explained just before, that here B atom will be here. As we know that a crystal will be the periodic repetition of the atoms, here B will be here, another atom will be here, another atom will be here. That means periodically the atom will be placed like this. Okay, so placed in the same direction would also scatter the radiation exactly in the phase with those scattered from A to B. So as we got the scattered radiation from A to B, from A is the scattered in this way, B on the scattered in this way. If we are going to consider the periodic lattice or periodic atoms in here like this, and on this plane it will be here, it will like this, then also the same phase, whatever the phase difference between these two we are going to get. Also, if suppose we are going to consider another atom will be here and this atom will be here, this also the same. If I am going to consider the diffraction from this atom, suppose this atom will be here and another atom will be here, the diffraction will be in that manner that the phase difference will be same as between these two rays. Okay, So same, so only for that this statement it has been written that as crystal is a periodic arrangement, here A, after that one atom, after that one atom, periodically arranged. Here we can consider periodically arranged. Then whatever the phase difference we found between these two rays, same phase difference we are going to be found from this atom and from this atom. Okay, as it is periodic arrangement, exactly in phase with those scattered from A and B. In 3D crystal, sorry, in 3D crystal, R may coincide with any of three crystallographic axes A, B and C. It can be possible that R, the position vectors from B to A, if we have to consider the 3D picture, then this vector may be coincide over A vector, crystallographic axis A or B or C, maybe. Thus, for the occurrence of the diffraction maximum, these three conditions should be satisfied simultaneously. What is the three conditions? It is interesting because previously we found that the so-called phase difference will be this much, should have to be integral multiple of, if it will be n of 2 pi, integral means n is the number and multiplied with 2 pi, if it will be equal to this much, if this much value will be equal to this much, then we can say that these two rays are going to be interfere with each other constructively. Okay, so hence if we have to consider in the 3D form of the crystal and the position vector may be A and maybe B and maybe C, separately along A, B, C we can write the three equations, this one. So instead of R over here, suppose if R will be considered as A, that means suppose this vector suppose A vector, crystallographic axis A, suppose. So instead of R I can write A. Suppose this from A, B to A, it is B, crystallographic axis B. Then I can write instead of R, B. Likewise I can write C instead of R. So three equations can be considered to finding or to represent or to accept that these two waves or the two scattered beams are going to be interfere constructively. So the so-called phase difference will be 2 pi by lambda A dot n will be equal to 2 pi h dash is equal to 2 pi nh. Why it is nh I am going to explain, wait. So likewise along B, along crystallographic axis B, it will be 2 pi by lambda B dot n. I am following this equation, right? I am following this equation, okay. So B dot n equal to 2 pi k dash equal to 2 pi nk. How it is nh, what is n, k, h, h, k, l, that I am going to explain, wait. So 2 pi by lambda c dot n equal to 2 pi L dash equal to 2 pi in lambda. Here h dash, k dash, L dash are represent any integers. Okay. So these are the conditions. These are the conditions. If we found, then we can say that these two rays are constructively interferes with each other. These equations all are named as equation number 3. Okay. To obtaining the equation number 3, here to obtaining the equation number 3, it has been assumed, we have been assumed that the atoms A and B, these two atoms, A and B are two adjacent nearest neighbors atoms. Okay. Hence the magnitude of A, B, C represent the interatomic distance along their respective crystallographic direction. Obviously, suppose if this atom and this atom will be said as nearest neighbors, then suppose we are going to consider a simple cubic structure. Suppose we are going to consider simple cubic structure. So this atom is this atom. If they are nearest neighbor and this will be the x-axis, then this is nothing more called the interatomic distance. And if this will be the nearest neighbor, so also this will be called as interatomic distance. Same thing we have been written, because here we have been considered to finding the equation number 3 has to, we are considered that these two atoms are nearest neighbor atoms. Okay. Hence, magnitude of A, B, C represent the interatomic distance along their respective crystallographic direction. Okay. Now, H dash, K dash, L dash. Here carefully you have to listen. Now, H dash, K dash, L dash and HKL. Here HKL, whatever we have been written, this is indicates the Miller indices. Indicates the Miller indices, whatever written over here, HKL. Okay. Differs only by a common factor n, which may be equal to or greater than unit. Hence, H dash, K dash, L dash can be written as NH, NK, NL respectively. What it is, that things I am going to be show to you. Wait. This is the one atom. This is one atom. We consider that these two atoms are nearest neighbors. So hence this will be, suppose this will be our y-axis. So this will be nothing but called as B. Interatomic spacing along y-axis, that is B. If it is cubic, then it will be A equal to B equal to C. So likewise, if these two atoms, suppose we have been considered, this will be nothing but the interatomic distance, that is A. Let if it is X direction. Okay. Now, if we have to consider from this to this, so the distance is A, right? So if we have to consider this plane and this plane, what will the distance between the two planes? What will the distance between the two planes? This distance D will be nothing but A. This distance will be D, will be nothing but A. Suppose we are going to consider another plane over here. Suppose we are going to consider another plane over here. So what will the distance from this atom? Suppose another atom will be here. This atom to this atom. This will be nothing but 2A, right? Or we can say 2 into D. Okay. So here, only for that, see here n, we are multiplying a integer n A. Okay. So this, suppose this Miller indices will be how much? This plane's Miller indices will be 1 0 0, right? And the Miller indices of this plane, which will be at the distance 2A, will be how much? Will be 2 0 0. You got my point? See here, H dash for this is 1. H dash for this plane or for this coordinate. Here is one atom. Suppose this is B and this is A. Whatever we have been considered for this one. So, and suppose B and A are along x-axis. Along x-axis, suppose. So B to A distance is how much? A. Okay. B to A interplanar spacing, if I am going to consider, then it will be D. And this plane is nothing but 1 0 0. Okay, that is nothing but HKL. Okay. So if we are going to consider this plane, then from here to here, the distance is what? How much? 2A. Okay. And this plane's Miller indices is how much? 2 0 0A. So the intercept over here, the intercept at here, if I am going to represent H dash, K dash, L dash, then this can also be written as, if intercept at this point will be written as H dash, K dash, L dash, it can be represented as some constant, some integer of H, some integer of K, some integer of L, of HKL, that is your the so-called HKL is the Miller indices, because here suppose here the HKL is the represents the any plane, so suppose arbitrary plane, so HKL is the represents the arbitrary plane, or suppose this HKL is represents the first plane. The second plane will be how much? It will be NH, NK and NL. Okay, so the corresponding intercept is H dash, K dash, L dash can be written as, here H dash can be written as NH, K dash can be written as NK, L dash can be written as NL. Okay, the same thing it has been written over here, that the corresponding intercepts, the so called intercepts H dash, K dash, L dash of any atom differs only by the common factor n, which may be equal to or greater than 1. So here if we have to consider the intercept for this plane, at here it will be 1 0 0 and the corresponding Miller indices is 1 1 1. Suppose we are going to consider here the intercept is 2 0 0 and the Miller indices is, this is, suppose this is HKL, suppose we have considered this is HKL, see, this is 1 0 0, sorry, this is HKL. So here I can consider 2 into H, 2 into K, 2 into L, like that. That I am going to be tell to you. Okay, so H dash, K dash, L dash, the so called intercepts which are in the form of integers can be written like NH, NK, NL, where HK, L here is nothing but your represents the Miller indices. So this equation will be 2 pi, instead of H dash it will be written as NH, NK and NL. Okay, now we have to consider alpha, beta, gamma be the angle between the scattering normal and the crystallographic axis A, B, C respectively. Now suppose this scattering vector, scattering normal, this one, this B to S is represents N, which is represents the scattering normal. Suppose this scattering normal angles alpha, beta, gamma with crystallographic axis A, B, C. Suppose this has been angle with this one. If I am going to be take over here, if this angle will be alpha, suppose, and this is the B to A is A vector crystallographic axis A, then A dot N will be A n cos alpha. Okay, and we know that magnitude of N we found how much here, magnitude of N how much we have been found over here, that is 2 sin theta. I am going to be put over there the A into 2 sin theta into cos alpha, that is from equation number 1 we found. This is from equation number 1, I have been substituted here as N equal to 2 sin theta. Now equation number 3, all the equation number 3, these equation number 3's values, what we can write? See, first here 2 pi got cancel, 2 pi and 2 pi got cancel. Okay, here also 2 pi got cancel. This will be A dot N equal to 2 pi lambda, sorry, lambda H dash, got it? A dot N will be equal to 2 pi got cancel, it will be lambda H dash is equal to NH lambda, this format. So in this format if I am going to write, so A dot N we found that A 2 sin theta cos alpha, A 2 sin theta cos alpha or 2A sin theta into cos alpha will be equal to H dash lambda. See, H dash lambda equal to NH lambda, H dash lambda, NH lambda. Similarly other equations, this and this will be written as B dot N will be this much, 2B sin theta into cos beta is equal to K dash lambda equal to NK lambda, C dot N equal to C sin theta into cos gamma equal to L dash lambda equal to N L lambda. Let these equations are equation number 4. The equations 4 is known as Laue's equations, which represent the conditions for constructive interference of diffracted beams. So oftenly in your exam, up to this much 6 mark questions is asking in your university exam. So if they will be asked that find out the Laue's equations, so you have to derive up to this much. But if additionally the question if asked to validate the Bragg's law, so here the rest of the part is that the validation of Bragg's law. We know that in orthogonal coordinate system, alpha, beta, gamma satisfy the condition is cos square alpha plus cos square beta plus cos square gamma is equal to 1. Let this equation number is 5. Here cos alpha, cos beta, cos gamma represent the direction cosines of the scattering normal n, because we have been considered that A vector, crystallographic A vector is angled with n as alpha, B with n beta, C with n equal to gamma. That we have been assumed. So direction cosines, so hence these are the direction cosines of the scattering angle n. Okay, n. Now what is the n now? Here n is nothing but is the same as the normal to the plane h scale, or that n is the, hence the interplanar spacing for h scale will be this one. Here I have been written previously discussed, means you can refer to our video whenever I have been explained the interplanar spacing distance of the lattice plane. I am going to be give the link of this discussions in the descriptions of this present video. You can go through this topic wherever previously we have been discussed. In this topic we have been discussed that the so-called interplanar spacing, suppose here one plane will be there and this will be the plane, the distance d, this distance from 0 to d is the interplanar distance, and this distance is here it is assumed that n is nothing but this distance. Here n is nothing but this distance, and this distance is angled with alpha with this x axis, beta with y axis, gamma with z axis. In detail I have been explained in that video, you can go through that video. And if we want to find out the interplanar spacing of for the plane h scale means suppose at origin one plane will be there and here another plane will be there. The intercept of this O to A will be equal to A by H, O to B, B by K, O to C, C by L, like that. Then D, this interplanar spacing will be nothing but A by H into cos alpha. Okay, because this will be the perpendicular and this will be the alpha. If I am going to consider cos alpha of this triangle OMA, then what will be the cos alpha value? This will be d O to M d by A by H, d by A by H. Hence d equal to A by H into cos alpha. Okay, so in detail I have been discussed in that video. You can go that video. I will give the link of that video in my description. So here d will be A by H cos alpha. Similarly d will be equal to B by K cos beta equal to C by L cos gamma. Let this equation number is 6. Okay, now we have to put A by H cos alpha. If A by H cos alpha, if d equal to d, if I am going to put in equation number 4, this equation number 4, this is the equation number 4. Okay, suppose you have to consider this equation. This equation will be nothing but how much? 2a sin theta cos alpha equal to nh lambda. So here we have to put as a cos alpha by h. So if I am going, we are going to do a by this a by h. Here I taken h over here. It will be sin theta into cos alpha will be equal to how much? n lambda. So here ah cos alpha, is going to be put as d. Okay, so if we will be going to do so, then here I written, no, here I written also. So here I am going to put that h, if I am going to take over here, then the a by h cos alpha, a by h cos alpha will be put as d, then it will be 2d sin theta equal to n lambda. Okay, so we found that the condition of the Bragg's law from the van Laue conditions. These are the van Laue conditions. By considering this these equations, we also verified the Bragg's condition here. Okay, so likewise also we can consider b by k cos beta and c by l cos gamma. For these two equations we are going to get the same. So this is the validation of the Bragg's law. So if the mark will be 8 mark questions will be up to this much, you have to write. So go through this video properly, and whatever the link I given for this interplanar spacing and Bragg's law, also you can go through those videos for your better clarity of your understanding. So thank you so much for watching this video. Thank you. If any doubt, you can contact with me. So thank you so much.